Everyone, my name is Erwin Giling. Today we are hosting at TNO here in Delft the workshop of the Perform project, reduction of CO2 footprint in the chemical industry. Is everyone able to hear my voice well? Any remarks in the chat? Yeah? Okay, thank you. So today we have a technical approach to the challenge, so we will explain the project and also explain all the technologies that we developed over the last year. And of course, there will be the lab tour. And I'm also happy to see a lot of you in person in this room. I guess you're all curious about what we realized in the lab and what equipment we have. And actually, it's currently running. I'm missing a couple of my colleagues who also should join, but they're running the pilot at the moment, so they're down in the lab. So for the agenda today, I will do an introduction. I guess it will be like 50 minutes, and then we have the presentation of Joost from VITO. We'll also have a short movie that we recorded in the laboratories of VITO, so you can also have an impression of how they're working over there. After the coffee break, we will have Riccardo, my colleague, do a more technical presentation on what we've been doing and all the results that we have reached with experiments in the lab and on the pilot. And then we will have a Q&A session, a discussion. So online, you can ask, I think, questions via chat. You can always do that. I think at any time, please, if you have a question in the room, raise your hand, or in the chat. Also raise your hand, I guess, or put your question in the chat and we will address the question. So then we plan to finish around 12 o'clock, the online session. Here we will have a lunch and then we will have a guided tour. And we can have also some further discussions on the technologies and all the challenges and the solutions that we have. All right, so let's start. Project overview. What is the Perform project? The Perform project is a Horizon 2020 project, which was started in January 2019. And it's now running for the 5th year, which is amazing. Normally, these projects run over 4 years. We've had some troubles with materials and realizing of pilot equipment. So in the end, we got a 1-year extension to be able to reach the goals of the projects. Well, the goals are to develop a power platform. This is a series of equipment that is integrated and which I will explain later on for the valorization of bio-based chemicals. It's very unique in Europe, 1 square meter electrode surface area, electrochemistry conversion with a production of 250 grams per hour. So it's about demonstration and also dissemination and exploitation. And actually now we're in the process of finishing the project. We're on the end, and that's also why we want to disseminate everything that we've done and learned. So why Perform and the motivation? I think most of you know this. We have a challenge, and we need to do the energy transition by electrification and reducing CO2 footprint in the chemical industry. On one side, we have to use decarbonized energy. On the other side, we have to use circular feedstock. And in our case, it's carbon from biomass. And combined, we have to make our products in the future in a sustainable and circular way. So this is our background. And this is why we built this project on the concept of using renewable feedstock, direct electrical conversion and separation purification of products, two-parts products, to high-value chemicals, monomers, and we use renewable power. This is the project structure. Actually, these are the work packages from feedstock analysis, development of electrodes, development of the whole system, the power platform in the end, and also we have to look, and we looked into exploitation and follow-up with respect to techno-economic analysis, business cases, and market development. This is the consortium. We are with now 11 partners from 7 countries. I think a lot of countries are even around the table. On the left side, we have the research parties over here, INSTM, VITO, TNO, University of Honheim. with sustainable innovation supporting us with exploitation and market assessment and communication, dissemination. Then on the right side, we have the companies, Avantium, EasyTech, Radici, Perstorp, Novamont, and Ava Biochem. And together, we are really a strong consortium with covering the whole chain from research of the basic concepts towards the commercial use and exploitation. So what are the key technology results? Let's focus on the technology today. It's a more technical workshop. To the right, there's a picture of the basic principle of electrochemistry. And in this case, we're doing paired electrosynthesis. It means that we have two kinds of feedstocks. And here you see an electrochemical cell with an anode and a cathode. In the cell, we convert the feedstock to a certain product, which is separated out in the DSP, so the downstream processing. And we do that on both sides. So we use the electrons efficiently. You could say we use them 2 times at the same time in one reactor. So why electrochemical? You have also other methods converting biomass. Well, it's about process intensification. Electrochemical conversion promises high selectivity and conversion rates. You can directly use the electrons in the conversion process, so it's integrated. Also, you have mild process conditions. You have not many problems with high pressures and high temperatures, and you can use flow chemistry instead of batch chemistry. This has its advantages, and Riccardo will go a bit more into that later on. So what we also did is develop new electrochemical electrodes, and we designed new reactors. We designed a new electrochemical process, and in the end, of course, we did build a complete demonstration line, which we call the Perform Power Platform. We worked on 2 showcases over the last years with feedstocks, peripheral levulinic acid and glucose. There's 2 lines. One line is the responsibility of TNO, and the other line of VITO. So you will see it also today. The TNO line is about going from peripheral to maleic acid on one side, and so that's an oxidation, and from levulinic acid to valeric acid for the reduction. The VITO line 2 is a little bit different, where you do a tandem reaction, first an oxidation from glucose to glyceric acid, and then from glyceric acid to adipic acid. The products, of course, then are maleic and valeric acids and adipic acids. And this has a number of applications and a huge market volume if you would make this work in an economic way. So these are the main activities and the development phases where we gone through over the years from 2019, starting with the feedstocks, the electrodes, the platform design, to platform integration, and also doing experiments on smaller scale in the lab to see if everything works. And then we are building the whole pilot platform last year, and this year we're into demonstration and showing that it also works. You see to the right the scale up, which is quite huge, I might say. We can be really proud that this scale up has been done in only 5 years. From we started with the 1 to 100 centimeter square electrode area, and now we're at 1 square meter electrode area. You could say this is TRL 3.4, where we started, and this is TRL 5.6, where we would end. So for some of these technologies, we take 3 TRL levels in one project, which has been quite a challenge and quite an adventure, so to say. So the expected impacts of our projects are in this slide. The electrochemical pilot that we are realizing. We expect to have an increased energy efficiency compared to the non-coupled electrochemical processes, because you're using the electrons 2 times, so to say. Development of electrocatalysts and electrodes with high faradic efficiency, so conversion to the desired products, and a low energy use. The downstream processing units, the way that we can separate out the carboxylic acids and the products from the electrochemical electrolytes, from the reaction mixtures with high recovery rates. We also did the techno-economic benchmarking, so get an idea of the OPEX and the CAPEX of the whole process. And we did work on dissemination, communication, and exploitation. So these are the main KPIs. So let's go through some highlights, high over of the different activities that we did in the project. Starting from the feedstocks, we developed several analytical methods and pre-treatment processes to be able to convert the feedstock. In this case, it would be a glucose. This was done mostly by Avancium and by VITO. We also use industrial grade feedstocks available on the market because there's a lot of companies already producing these feedstocks for the demonstration. And that is the case, for example, for the furfural we're using. We're using commercial feedstocks for that. With respect to catalyst and electrode development, we put a huge effort in trying to get better and more selective and more stable electrode materials. The partners working on these are INSTM, Avancium, and VITO. There's one thing that we discovered, especially for line 2, is that electrolysis to adipic acid is very challenging. And it will not be, we didn't find a good catalyst for that step. But there might be other ways to convert to glutaric acid, which is still working to adipic acid. So that is one of the challenging things that we encountered. On the other hand, we did work on novel cathode and anode materials for the other reactions, and we also proved that we can do electrode scale up to 1,000 centimeters square electrode. So this is how scale up works. You start very small in electrochemistry, and then you go to bigger steps, bigger reactors. And this was 2 years ago, and now we're here. So this is a 1,000 centimeter square reactor that was built by Hisitech, and also this pilot here, the 1 square meter stack reactor in the middle, which you can see downstairs later today if you're here. Was built by Hisitech and designed both by TNO, Hisitech, and VITO. So this is how we worked over the years, and you see that you actually are going from very low TRL levels for new electrode materials to TRL 5-6 pilot in this way with increased surface area and increased productivity. This also involved a lot of process development, especially for the downstream processing. You have to separate out your products, you have to recover your products. And the idea is also to generate samples in an early stage in the project already. And then in the later stage, you can generate samples in 100 grams and kilogram scale. So this is that we all did. Later today, Riccardo will tell you a bit more about this. So this is one slide with all the equipment that we have right now, and which can be used for these reactions, but also for different reactions. I just mentioned electrodialysis, concentration, crystallization equipment, liquid extraction. We have a distillation setup, and in the end, then you go to a target product. In this case, I think these are maleic acid crystals. So, for example, one slide is a showcase where we go from furfural to maleic acid. This was done on the 1,000 centimeter square reactor. Just to prove that this can be done. We had a yield of the intermediate plus the maleic acid of 80% with a 99% conversion and a 70% ferritic efficiency. So that's the measure of how many electrons and energy goes into the product. We showed that we can do the separation, the pre-concentration, the cooling crystallization, and we got quite some purity here. You see after several steps that you can get after drying to these still slightly brown maleic acid crystals. So it's not 100% pure, but it's very good quality already. On the process assessment, techno-economics and LCA, we have University of Hohenheim, Ava Bijtram working, but also input from our industrial partners. Working on environmental life cycle assessment, because you have to know if you would scale this up further to big scale, what the CO2 reduction would be, what the cost would be, what the impact would be on the environment. So this has been done based on initial estimates of our KPIs and also the KPIs that we are reaching right now. There's a model behind that. I won't go into the details, but it's always very important to do in your project. Then follows from the techno-economics, the business case analysis, and this was based on the results somewhere in the middle of the project, where we show that we have a potential for a positive business case for maleic acid if we could reach the target performance, which we're almost reaching right now. And you can look at the sensitivity analysis in the graph that this is the current density, so that's the number of electrons that you could put in your electrolyzer per surface area. And this is the OPEX and CAPEX. I think this is the total levelized cost in this case of maleic acid. You can see that if you increase the current density with the same order of magnitude, so the same size of reactor and equipment, your costs go down. But there's also an optimum. At a certain point, you don't want to increase the current density anymore. We are now in this area around 100. And then you get to the 1.1.2 euro per kilogram already, which is starting to look attractive from a business perspective. But yeah, there's also a remark always that the business case strongly depends on the future price of feedstock, energy, but also material costs. We've seen over the last years that even buying components, equipment, the price of building pilots and factories has raised tremendously. So we have to continuously adjust the business case and your models with the current prices on the market of your materials, your feedstocks, your energy. So that's what we're still doing and finalizing towards the end of the project. So summarized from my side, we showed that electrochemical conversion and integrated downstream processing is possible at the lab scale. And we're also currently demonstrating it at a pilot scale. You see the picture over here. This is a picture from the setups in the lab below, the upstream pilot and the electrodialysis unit. So we created in the project a flexible electrochemical reactor stack with different testing possibilities. We can use this also for different reactions. If you are an industrial partner or a company or a research partner who wants to develop a new reaction, organic synthesis, we have all the equipment from Perform to help scale this up. It's modular, it's integrated, but it's still modular. You can change different units. It's also skid-based. You could even move it to another location, put it for a demonstration at the company side, hook it up with different processes. That's also why we say it's open access. This is also a requirement of the EU, that it will be available after the project in the future. So that's also offered to the market, so to say, right now. Now, well, currently the line 1 campaign is running in the TNO labs below, and we will see how that ends up. And also Riccardo will tell a bit more later in his presentation this afternoon about what's happening over there. I think, yeah, that's it. I think I took all my time. Thank you very much. If there's any questions now, we can also do it later. Any questions online? No? So then we can go back to the agenda, if that would work. Apparently not. But yeah. We need a presentation of Joost.
Can you do it from your computer?
Yeah, it can. But then I'll need to. Yeah, okay, that's it. Need an USB. I still have an USB. Yep. Yeah. And then we have to go to VITO. And then this one.
The video.
All right. That should work. I think I can close this one for now. Yeah. Sharing has stopped, so we have to share screen in this one. Here. And go to full screen. And then do duplicate. Yeah. I think you're good to go, yes.
Beautiful, thank you.
You can stand up, but if you sit down, it's easier to.
Yeah, I think so.
To work online.
Yeah.
Yeah.
Okay, good morning, everyone, here at Delft and online. I will give you a short overview of what has been a long trajectory, as Erwin already mentioned, in the Perform project. Already 5 years almost of searching and testing catalysts, processes. And specifically for this presentation, I want to focus on the conversion of glucose to glucaric acid and finally to adipic acid. So, which is actually line 2, as Erwin mentioned. I hope the sound is okay, right? I mean, I will, unless you indicate, I will continue. Okay, so this figure you just seen as well in the previous presentation. This is the initial project concept for line 2, where we want to start from glucose as a feedstock and do a paired tandem electrosynthesis, which means that in the first stage we will convert glucose to glucaric acid which is an oxidation step. And then use the glucaric acid in a tandem way to produce adipic acid in the following reduction step. As you will see during the presentation, it is, especially the second step, is less obvious as it may seem. But let's first now focus on the first step. So the oxidation of glucose to glucaric acid. In fact, what is glucaric acid? It's a diacid with 6 carbons, which at this moment has a, let's say, currently a very underdeveloped but still growing market, used in detergents, spreaders for lowering surface tension, etc., and also as a food additive. The projected market in 2027, but this is already a projection from a few years ago, would be $1.5 billion. But this is, of course, with a lot of uncertainty. Currently, it's being produced in biocatalytic, catalytic, or electrocatalytic way, but either with very slow rates, low selectivities, high DSP costs, or capex, and especially the electrocatalytic way seems to provide an opportunity to decrease the capex and opex of the process. So in the Perform project, we studied the electrocatalytic oxidation and also the upscaling. So did both the lab scale work and also the upscaled process. And the idea is indeed to combine a renewable feed with renewable energy. So the glucose coming from cellulosic biomass feedstock as a renewable feedstock. And of course, the electrocatalytic process can be plugged into a renewable energy system. So this is a double bonus, let's say, for this process. There was an existing process patented by Renovia, which was a thermocatalytic process based on gold, platinum, and palladium catalysts with supply of oxygen, which also indicated a lower capex and opex and energy and impact possibility. But we wanted to focus, of course, in this project on the electrocatalytic conversion. And therefore, we needed to find electrocatalysts which was not very commonly at the time when we were starting the project. There was a lot of information on full oxidation of glucose in fuel cells, but very little on the actual electrocatalytic oxidation in electrolytic cells. One particular example would be the use of porous manganese oxide titanium electrodes, which was reported in 2014, but which actually had a very low yield and also used diluted glucose concentrations, so not very suitable for the actual industrial process. And there was also some indications of tempo-mediated oxidation of glucose with reasonable yields of 85% reported. Later on, when we continued the project, more and more papers were actually published on this topic, as you can see below. And this also included, again, the use of gold electrodes, but also a fairly new one, nickel iron oxide catalyst on nickel foam, which actually produced very high yields and Faradaic efficiencies, which were reported in Nature Communication. Also in Chem Electrochem, there was an important publication on this topic. So in terms of reaction mechanisms, how does glucose oxidation proceed? The first intermediate that is formed on the surface of the catalyst is actually gluconic acid, which is a monoacid. So one carbon of the glucose molecule is being oxidized to carboxylic acid, and in further steps converted to a diacid, so the glucaric acid. Several byproducts are also possible. So there is a possibility of the hydroxysuccinic acid, also butanoic acid and oxalic acid, but also other products can occur, like tartaric acid is also found sometimes. What is known on the conditions is that strong alkaline conditions and diluted glucose solutions prevent the formation of heavier products, so that would be beneficial. But it's difficult to, of course, use diluted glucose solutions in an industrial application. Another thing is the stability of electrocatalyst is inherently difficult, since diacids are very good complexing agents, managing to complex metals quite easily. So where we started was with a catalyst screening for this reaction, so for the glucose to glucaric. First, of course, is the mixture of gluconic and glucaric acid. And there were several electrocatalysts prepared by partner INSTM based on gold, palladium, and all these were deposited onto carbon nanotubes as nanoparticles. But for most cases, I'm summarizing this now, but for most cases we saw very little to no yield of glucaric acid and only small amounts of gluconic acid to be formed. On the other end, when we tried using the tempo-mediated approach in bicarbonate or in carbonate solution, we found initial at least some yields to glucaric acid and a lot to gluconic actually. So tempo-mediated oxidation, how does that work? You have the radical, the tempo radical, which is actually oxidized to the positive ion, as you can see in this picture, and this reacts with the primary alcohol on, for example, a glucose molecule. So then the tempo is again reduced to the OH form and can be recycled at the electrode surface. So initially, these tests that we did on a very small scale, so this, what Erwin also showed in his presentation, the first step with H cells, we saw no poisoning of the electrode. We also see that there's a high stability of the mediator, so it doesn't get broken down at the anode. And we have a very high reactivity and turnover frequency. Of course, mediated electrolysis always implies an issue of separation, and also in this case, the tempo is a organic mediator or catalyst, which is difficult, of course, to separate from the electrolyte as it fully solubilizes and it's needs to be taken care of. One of the first things that we tried to investigate was to actually immobilize the tempo onto the electrode surface, and therefore we used a specific form of tempo, which was amino tempo. So you have the amino group. Control L. And trying to find the pointer. No. This is a pen. Okay, so we have the amino group located here in the tempo molecule. And the idea was to form a amide bond together with the carboxylic groups on a carbon surface being the electrode surface. And then the idea was to immobilize the tempo in this way. In fact, we tried different types of carbon materials, electrochemical immobilization time, and also concentration of amino tempo. But the best result we got was only capable of really converting glucose to gluconic acid. So the first oxidation step, basically. No glucaric acid was found. So we again were in a situation where we needed to deal with the mediator, so the tempo, which was successful in oxidizing glucose to glucaric acid, but we needed to take care of the downstream processing. We did some additional tests, of course. So after H cells, the next step would be to use microflow cells, where you use really flow chemistry in a more realistic cell if compared to a industrial size stack, for example. This is already, especially in terms of flow dynamics, more adjacent to the final stack. In this microflow cells, we adjusted different variables, tempo concentration, the temperature. We also tested different anode materials, all carbon-based materials, since we wanted to involve low-cost materials in our process. What was one of the conclusions basically of this screening was that we get the highest conversion to glucaric acid with some non-woven electrodes, which we selected then for further testing. And we found also little to no dependence on the tempo concentration, ranging from 20 to 100% mole percent tempo. 100 mole percent, of course, being the same concentration as the initial glucose concentration. When we conducted a test, this is what a batch test would look like. So you can see the yields of gluconic and glucaric acid. But what's important here is to note that there is a average current density of 15 to 20 milliamps per square centimeter. In terms of standard electrolysis, or let's say water electrolysis, is of course very low, but in organic electrochemistry, this is a reasonable figure, let's say. We had a Faraday efficiency of around 60% towards glucaric acid and a yield of almost 60%. So we see in this graph also that the maximum conversion happens during the first 3 hours, where initially the glucose is converted to gluconic, and then later on the reaction from gluconic to glucaric picks up. From this small scale flow cell, actually we scaled up together with partner HyCTech to a 1,000 square centimeter cell, which was constructed by HyCTech. So this is a single cell that we used for testing, and which is also basically the blueprint for the perform pilot reactors. So we started with 100% glucose addition, so no introduction of any impurities at this point. And we did a performance testing with the non-woven activated carbon fiber. We used in this case 100% temple, and we determined the optimal glucose concentration in the analyte. Some of the practical issues may be important to note also, things that we see, because of course upscaling involves also introduction of a lot of practical problems. So one thing was that the cell actually was kind of, there were some leaks, let's say, at the initial stage due to the fact that the end flanges were warped a little bit when it was assembled. This was just adjusted by using external clamps to provide sufficient pressure on the center part of the cell. Another thing is that we nickel plated the anodes to prevent passivation of the current collector there. And then we used this cell with two continuous loops, so anodic and cathodic loop. It was connected to a pilot installation with a 110 volt power supply, control of the pH of the analyte, and constant cell potential was applied. At first, we were using a batch mode, so we started with a typical glucose concentration and just let the reaction evolve. But later on, we also used continuous addition of glucose to monitor and monitor the reaction. So in this case, this is the graph, actually the results of the continuous feed experiment. So where we used the cell in a continuous mode. This is just by adding glucose in a concentrated way at a rate of 300 millimoles per hour. And as you can see, the total yield here is quite large, but it consists of a yield of around 40 to 50% of gluconic acid and also glucaric acid. When we look at reaction rates, we see that especially the rate of the gluconic acid, so the monoacid, is following a lot the glucose profile, of course, the glucose concentration, and the reaction rate of the glucaric acid actually starts to increase when gluconic slowly is decreasing after some time. It takes more time for the glucaric acid to form. We did the same thing, the same experiment also for a continuous feed at 600 millimoles per hour. And as you can see, of course, the yield is a little bit lower due to the fact that we have some unreacted glucose still. So actually, you could say that in this case, the feed was a little bit over dimensioned. So I mentioned already tempo as a mediator necessary to, of course, separate from the reaction mixture again. So the first step that we thought of to separate the tempo was the use of electrodialysis, and at the same time also separate glucaric and gluconic from the reaction mixture. Electrodialysis is also a electrode-driven process, so fits quite well in the whole idea of plugging in this into renewable energy systems, renewable energy electricity. It operates with a stack also consisting of an alternating anion and cation exchange membranes. And tests were conducted in microflow cells, in this case, where we see that we can actually have a very good current efficiency for different type of membranes. And we have a very good separation of glucose and gluconic and glucaric acid. So the glucose is actually separated, or the gluconic and glucaric acid are separated very well from the glucose. But in this case, with just conventional electrodialysis, also the electrolyte is removed. Electrolyte being in alkaline, for example, potassium hydroxide. Membranes perform equally good in the sense that we tested a range of membranes from different suppliers, and also had an estimation on the energy usage during operation of the electrodialysis. But in order to overcome the issue of electrolytes, which is actually spent together with the gluconic and glucaric acids, we switched to a 3-compartment electrodialysis, so not a conventional one, but a 3-compartment with a bipolar membrane, which allowed us on one side to separate the acids, gluconic and glucaric, together in an acidic compartment at their natural pH, let's say, and on the other end also recover the alkaline electrolyte, so the potassium hydroxide in this case. The next step in the DSP would be a crystallization step. So from the electrodialysis, we get a concentrated mixture of acids. And the first step there would be a cooling crystallization, where some of the potassium monoglucarate in this case would crystallize already. To enhance crystallization, to actually lower the solubility in a sense, an anti-solvent was also used to decrease the solubility and increase the crystallization even more. And as you can see here, there were initial promising results with isopropanol, but when the study was extended to other alcohols, and especially with methanol, we were able to achieve very high yields of recovery for glucaric acid 80% and a selectivity of 10% just in a single crystallization step. The nice thing with methanol is that you can also use it subsequently to wash any precipitates that are formed and further increase the purity even with a factor of 22. So this provided a very solid DSP route, let's say, to purify, to separate and to purify the glucaric acid from the reaction mixture. And this is how a DSP scheme, together with the reactor, of course, would look like. So in this case, This is the electrocatalytic reactor where glucose is reacted with the tempo to in alkaline conditions and is oxidized to gluconic acid and glucaric acid. This goes into a electrodialysis, so the 3 compartments set up with bipolar membranes, and we get on one hand a return of the acids as a combination of gluconic and glucaric acid, which is sent into a crystallizer, where some of the crystals already precipitate and can be further moved downward to the washing step. The remaining liquids can then be further extracted, the acids with the methanol, and all the methanol fractions, let's say, can also be recovered in a distillation step. In this way, you could operate the process of glucose oxidation in a continuous way with recovery of virtually all the effluent streams and electrolytes. We did a test also coupled, so the reactor coupled to this electrodialysis with the bipolar membranes as a first step. So the let's say this whole process was then cut off here. So we have the reactor plus the electrodialysis with the bipolar membranes, and there we see that in fact in the analytes we see that the gluconic and glucaric acids concentrations are increasing, and after some time we switch on the electrodialysis, and you can see that it's automatically has an effect on the gluconic acid concentration. Meanwhile, of course, this is a continuous fed experiment, so there will be some stabilization of the gluconic acid in the reaction mixture. So this is actually the analyte concentration. On the other hand, if we look at the acidic compartment of the electrodialysis, we see definitely no glucose entering there. So we have a perfect separation of glucose and the acids, and you can see that the concentration of acids is increasing in the acid compartment of the electrodialysis. So in conclusion, for the first part of the reaction, the oxidation of glucose, tempo is a well-performing electrocatalyst. It is a mediator, of course, and needs to be recovered. But we have reasonable yields and efficiencies, and we're able to also scale up to 1,000 square centimeter, which is approximately 20 grams per hour. And both the electrodialysis and the two-step crystallization with the anti-solvent precipitation really make it a powerful downstream processing when this actually the process can be used in a sustainable way in such that it will not provide any significant waste streams. I still have a little bit of time, I think, to talk about the second part of this line. So actually we have now glucaric acids, but we want to convert it to adipic acid. And then Erwin already mentioned that this was a very difficult, non-straightforward reaction. So in terms of adipic acids, of course, the market is huge and is existing. It can be, if we were able to make adipic acid in this way, there would be a direct plug-in of our product. Used mainly for nylon 6,6 production, polyester resins, food additives, whatnot. And currently, the existing process for adipic acid is a very detrimental one, so fossil-based, very energy intensive, and also producing lots of waste streams, especially nitrous oxides, which are damaging a lot and enhancing climate change, of course. In terms of electrocatalysts, for the route of glucaric acid to adipic acid, not really any electrocata were known at the start of the project. So there was some literature on thermocatalytic conversion of glucaric acid to adipic, but the initial idea was to use this knowledge actually to convert it to produce electrocatalysts. Unfortunately, this was not so very straightforward, and we also tested a lot of other metals. We did actually a high throughput screening, so to say, in terms of metals that were tested and electrolytes in different combinations, and none of them actually really provided any adipic acid. This is all done in aqueous environment, and this is also one of the issues that we found later on, of course. Then some time ago, I think 2020, there was quite a significant publication in Angewandte Chemie, where a group actually found a palladium vanadium oxide catalyst, which was immobilized on activated carbon, and which produced a high yield of adipic acid. Also, again, thermocatalytic route from glucaric acid to adipic acid. So you need a hydrogenation step with 20 bars of hydrogen and elevated temperature of 110. But it was pointed out like this. And the first thing that we did, and actually partner Radici proved this, that it was possible to reproduce this in combination with the catalysts that were provided by INSTM. So for the thermocatalytic route, this could provide a solution going from glucaric to adipic acid. First attempts to also use these kind of catalysts in an electrocatalytic way were not successful. So then we took a few steps back and tested a few substrates which were similar to glucaric acid, and tried different types of catalysts, electrocatalysts, in these very small cells. So as you can see, the scale has to come down again due to the fact that we did not have any good solution yet for the electrocatalytic conversion. We did a lot of screenings with different electrodes and metal oxides in specific electrochemical conditions. And then there was one, so we tested these compounds, basically glucaric acid, tartaric acid, and hydrobenzoin. And for hydrobenzoin, which is actually a model, could be considered as a model compound for the electroreduction of these vicinal hydroxyl groups, as we have in glucaric acid. The hydrobenzoin actually gave good results towards the product. So in these specific electrochemical conditions with the catalyst that we selected, we see that, first of all, we see when the catalyst is activated in terms of the electrochemical conditions, the potential. And we also see that the reaction mixture, so the hydrobenzoin actually gets converted to trans stilbene. Stilbene is actually the compound that we are looking for, in the sense that this is the compound which eradicates the hydroxyl groups from the backbone. Another thing is that for this reaction, also the solvent was very crucial. So a specific solvent that we used provided the trans-stilbene, but if we use, for example, acetonitrile, we arrived with completely different compounds. So this, to sum up, this very recent part of the research on the glyceric acid to adipic acid still needs to be developed further. The metal oxide catalysts that we used seem to work on the hydrobenzoin, and we need to now check if it's also working on the tartaric acid and then also the glyceric acid. We will, of course, keep on investigating the electrochemical reaction, the kinetics, and try to modify also the surface of the catalyst by immobilizing this metal oxide onto a catalytic surface. Of course, reaction optimization still needs to be done, so this is a bit earlier stage, let's say, and still needs to be developed. One thing I wanted to still mention here is also that we will, and INSTM still is developing further the palladium and rhenium oxide electrocatalysts, so there is still more to be expected from that side. And then finally, of course, paired electrolysis, as it was initially devised in the concept, will be a difficult one, since this reaction typically floats in organic solvents, and the oxidation reaction is an aqueous electro oxidation. It will be difficult to pair, but at least if it can be shown that the electro reduction of glyceric acid to adipic acid works, this would be already a fantastic milestone. And eventually, if we succeed, then we can think of scaling up and optimizing the process further, as we did with the oxidation reaction. Okay, so this is basically the end of my talk, and if you have any questions, you can contact either one of us or, of course, the other partners in the consortium. Thank you.
Thank you, Joost.
Thank you.
First question.
Sure.
How much time do you think you need for that additional research? And manage it within this?
It will not be completed within this project, no. But this is on our strategic agenda as well, so we will continue even after Perform finishes. Yeah.
So probably maybe to start another project in the consortium, or to make the next step.
It's a route we can think
Yeah.
of. Yes, absolutely. Yeah.
Okay.
You have to share that window.
There's also
Yeah.
always what also the EU prefers, say to start, have something and to work it real out
Yeah.
to the next stage. Next step.
Yeah. The main objective of Perform would be to provide a sustainable alternative to certain chemical processes, to chemical industry in general. One way we can do this is by using a different feedstock. In the case of Perform, we switch to a bio-based feedstock. So we take away the fossil-based feedstock in classical or conventional chemical industry, and we replace it by a bio-based feedstock. And on the other hand, we're also focusing on electrification. So electrifying the process, converting the bio-based feedstock in an electrochemical process to the desired components. VITO's role in this project is mainly on the development and demonstration of one specific reaction. And this reaction is the conversion of glucose to glucaric acid and finally to adipic acid. Adipic acid is a compound which is readily used in chemical industry and mainly in polymer industry for the synthesis of nylon 6,6, a very common polymer. And what VITO actually focuses on is first the oxidation of glucose to glucaric acid, and in the subsequent step we will develop also the reduction of glucaric acid to adipic acid, the desired component basically. So we will develop the reaction, the electrochemical reaction in this process, but we will also focus on the DSP, the downstream processing so-called, which is the separation and the purification of the component that we form. Gluconic acid and glucaric acid are formed in our reactor and are separated by a process called electrodialysis. Electrodialysis actually selectively takes out glucaric acid and gluconic acid from our reaction mixture, and that's what we further will use for the separation and for the purification. This concentrate of gluconic and glucaric acid will then be transformed to a cooling crystallizer, and there we will drop the temperature, limiting the solubility of the glucaric acid and therefore creating also precipitates and pure glucaric acid crystals. To further increase the separation efficiency, we add another anti-solvent, we call it. Actually, it's a solvent that is used to lower the solubility of the glucaric acid in this mixture, which further increases the productivity of this separation. All these crystals can then be collected from the different process steps, and they can be further purified by using this anti-solvent to wash them. And all the washing water, all the washing liquid basically, which contains water but also the anti-solvent, can be recovered by distillation in a subsequent step. So the main benefits of the Perform process are twofold. On the one hand, we use a carbon neutral feedstock, glucose, for example, derived from cellulose. And on the other hand, we can plug in our process into the renewable energy grids. So organic electrochemistry is still quite young. During the past 5 years, very promising results have been shown in literature as well. Upscaling is quite new and still many hurdles need to be taken, but the prospects of developing a sustainable and carbon neutral process to the existing fossil-based route is very rewarding and should be really explored further.
And it's very important for industry and for academic world is how to convert selectively glucose to glucaric acid. And it's a very challenging project.
Test 1, 2, 3. Welcome back. Are you all good? And then you have the pointer. And then you have the floor. Thank you.
Hello everybody, welcome back. My name is Riccardo Zaffaroni from TNO, and with this presentation I will tell you something more about what we have done in line 1 of Perform. So first of all, maybe a bit of the motivation. Motivation for this project is electrification of the chemical industry, and this is really important because we need to get away from fossil-based feedstocks, and we need to go to more renewable feedstock. So this is one of the targets of Perform. So start from renewable feedstocks and renewable electricity. Renewable electricity is something that is available pretty much everywhere, and we need to find a way to use it to make our transformations. So with that said, if we use feedstocks that are renewable and renewable electricity, then we can reduce CO2 footprint from the chemical industry, and maybe even help us staying within the Paris Agreement of 1.5 degrees target and becoming carbon neutral by 2050. So how do we use renewable electricity to do chemical transformations? So this is done with electrochemistry, and electrochemistry is the use of an electrical current to perform chemical reactions that are not spontaneous. I guess the example that everybody has in mind is water electrolysis, where you have an electrochemical cell with an anode and cathode, maybe even a membrane. And on one side of the cell, at the anode, you apply some potential and you generate oxygen by splitting water. And on the other side, you generate hydrogen, again, by splitting water or recombining the protons and the electrons that are generated at the anode. So with this is a very nice example of, let's say, producing a fuel, in this case, hydrogen, by using electricity. But so how do we translate this to, well, other type of chemistry? Well, in general, instead of, let's say, using water as a feedstock, we can choose raw material, different raw material, maybe even two different ones, and then we can feed them again to the two sides of the cell. And on one side we will, let's say, reduce the material. On the other side we will oxidize the material, and then we generate products. So in this way, in the water electrolysis, for example, what we generate is hydrogen, which is a fuel, but on the other side we generate oxygen, which has very, very poor economic value, because typically it's just dumped in the atmosphere, and it's not marketable compound. But if you actually manage to choose two different materials that can be both reduced and oxidized to relevant compounds, then your business case is going to go a bit better, because now you have two valuable materials that you can market. And by the way, this is done for the same electricity, because on one side you use electrons and on the other side you generate electrons. And so for the same amount of electricity, you generate two products. So how do we choose? So I said, like, we need to choose raw materials. In the case of Perform, maybe we take a step back and we choose the products that we want to make, and then we walk back to the raw materials. So in case of Perform, we said to produce on one side of the cell, on the oxidation side, maleic acid. Why maleic acid? Well, maleic acid is used pretty much in every field of chemistry, going from lubricants, surface coatings, even like polymers, agricultural chemicals. So it's really very, very wide spread chemicals with huge market. And if you look at how it is made commercially at this point in time, is a vapor phase oxidation of well, benzene or butene, anyway, like fossil-based feedstock, using oxygen as an oxidant. Typical reaction conditions are like 400 to 500 degrees. You use a catalyst that is based on vanadium, which is not very abundant metal. You have a very low yield, and as a byproduct, because the high temperature that you apply, you generate quite a lot of CO and CO2 byproducts that, of course, don't help the climate change. On the other side, we choose to make valeric acid. Again, this is something that has a very big market in general for perfumes, cosmetics, or even like food additives, because you can make the ester of valeric acid, and that is, you know, very, very pleasant compounds, as opposed to valeric acid. Again, if you look how it is made commercially, it's made by the OXO process. Here we're talking about homogeneous catalysis, typically based on ruthenium catalyst with well, very fancy ligands around. And as we heard before from Joost, if you have a homogeneous catalyst in solution, then you also need to deal with the recovery of the catalyst and remaking the catalyst, because some of it will decompose and so on and so forth. So this
these two examples are nice molecules that can be that would be valuable to be produced in a green fashion. But at the moment, there is no green alternatives on the market. So how do we do that in the Perform project? So we walk back a bit from the products. We choose renewable feedstocks that are available that can actually be converted by electrochemistry into desired products. So now we have furfural as a starting material on the oxidation side. So we carry out an oxidation to maleic acid, and on the other side, we have a levulinic acid feedstock that can be reduced to valeric. Both these reactions are happening in the same electrochemical cell. So in this way, again, we produce two different products for the same amount of electricity within the same setup. So the benefits of this process, of course, everything is based on bio-based renewable feedstocks. We only use electricity as a driving force to carry out the reaction. There is no CO2 that is emitted, other than, well, some of it due to the actual reaction. Maybe I will come back to that a bit later. Typically, like these electrochemical processes are run at atmospheric pressure and at room temperature, so we don't even need like extra energy for increasing the temperature or pressure. And then when we go and look at the business case, now we have for the same capital cost and operational cost, we have two different products that can actually make a positive business case. So if we take a bit of from the start of the project to the actual to the actual pilot that is now in the labs. So we started with a reaction and catalyst development. Once we actually knew a bit more the reaction that we wanted to carry out, we scaled up to 1,000 square centimeters. Well, 100 square centimeters, 1,000 square centimeters, and then we went to demonstration pilot. This because within the project we have a productivity target of 250 grams per hour, which is about 6 kilograms of product per day, with a certain per day efficiency. But also target of the project is the purification. So once you have made your product with electrochemistry, then you also need to get rid of let's say electrolyte impurities and go to purified chemicals. Together with that, we also want to demonstrate the reusability of the electrolyte. So after we take out our products, we reuse the same electrolyte in the process to show that we have a full closed cycle. And I'm going to go a bit more into the details of every step. So initially, you start typically with a catalyst selection, and I will focus more on the furfural to maleic acid side, but the same reasoning can actually be done for the levulinic to valeric. So initially, we need to find an electrocatalyst that can carry out the electrochemical reaction that we want. And we tested quite a lot of different materials, different transition metals, precious metals or not. This can be done in a very, very small scale, typically like few milliliters with an electrode. And you get graphs that look like that, and you look at the difference between when you have furfural in solution and when you don't have furfural in solution. So in the case of the red curve, you see that around 2 volts potential, you have an increase in current, and that's your furfural oxidation. One other thing to be careful is that once you have chosen your catalyst, you need to make sure that your catalyst is not active at decomposing your product. So in this case, you look at the maleic acid as a product, So if you check again the same voltammogram, when you have maleic acid in solution, you see now that the blue line and the red lines are overlapped, meaning that your catalyst is not doing anything with the substrate or the product that you have produced. So within this research, what we figured out is that well, platinum of course works nice for doing this this reaction, this oxidation. However, we also found that lead oxide works quite well, actually even better than platinum. And lead is quite nice material that is already used a lot in industry as a well, as a catalyst. So we actually settled for lead as a main working catalyst. Once you know something about your catalyst, you also typically would like to investigate a bit about the mechanism of your reaction, because maybe the mechanism is influenced, so the product that you make is influenced by the actual electrolyte properties. In this case, if you look at the effect of pH, if you carry out this reaction, this oxidation from furfural on well, a catalyst, if you do it in acidic conditions, you do get maleic acid as a product. However, when you do it in alkaline conditions, you get something different that might be desirable or not, but it's not the product that we are targeting. So in this case, we did settle for an acidic electrolyte, because maleic acid is the product that we wanted. And then we went a bit on to carry out a bit of mechanism investigation, because when we carry out this oxidation reaction from furfural, what is happening is that we see something different than maleic acid. Or let me rephrase that, together with maleic acid, we see some other intermediates. And specifically, we see this 5-hydroxyfuranone being produced as well. So for us was a bit important to figure out whether this proposed mechanism is what is actually happening in our reaction. So we did a bunch of different tests to figure out whether like this 5-hydroxyfuranone can also be oxidized electrochemically still on lead oxide to go to maleic acid. And indeed, we find that if we start exclusively from 5-hydroxyfuranone, then we can actually convert that to maleic acid. So I want to point out here that if you look at the actual mechanism, at some point you also have the formation. I don't know what's happening. You also get the formation of formic acid, and this formic acid is actually in equimolar amount with the furfural that you start from. Formic acid is also like an excellent molecule to be made. Within the Perform project, we did not focus on the recovery of formic acid, but envisioning like bringing this to market parties. Maybe the recovery of formic acid can be something valuable to lower even more or to make a better business case. Yeah, so now that we know a bit of the reaction mechanism, we also want to know something about you know, temperature, electrolyte strength, and so on and so forth. So we did a bit more screening, doing the same reaction at different temperatures. And for example, we see that if we carry out the reaction at 20 degrees, we have quite a lot of let's say yield and Faraday efficiency. They're in the very high range. If you combine maleic acid and 5-HFO, and in this case they are combined because we know that we can convert 5-HFO to maleic acid, so it's really an intermediate. We are in the like 70% yield with about 90% Faraday efficiency. When we increase the temperature, we lower considerably the yield of the reaction. So this is really pointing to the direction that we should operate at lower temperatures to have better conversions. Similarly, we also looked at the electrolyte strength. So I said that we are working in acidic conditions. So if we use a 50 millimolar or 200 millimolar sulfuric acid electrolyte, then we also see that at 50 millimolar we get better results compared to the 200 millimolar. So with all the when you combine all these informations that are actually gathered from a very small setups, typically like H cell or smaller 10 square centimeter flow cell, then you have sufficient information to move to the next step. And the next step is indeed scaling up from these tiny setups to a bit bigger setups where different parameters come into play. For example, now you have a flow cell that has certain geometry. You need to optimize a bit the geometry. You need to optimize a bit the electrodes that you want to put in, whether you use plates, whether you use metallic foams, the thickness between the anode and cathode, like all these sort of parameters are becoming really relevant in this intermediate phase to then be able to scale up even further. With a bit of calculations and experience, then we turn to our partner EasyTech to build a 1,000 square centimeter cell that we can use as a let's say a preliminary cell to do a proof of concept. And indeed, when we use the cell, we have quite a lot of good results. We have a conversion of furfural that is almost quantitative. We can get about 80% yield of maleic acid plus the intermediate, high selectivity, decent Faraday efficiency, well, now with these results in hand, we are really ready to scale up even further to the full pilot setup. So with this 1,000 square centimeter cell, we can reach about 50 grams per hour of product, but that's not sufficient to cover our target. So then we turn to this pilot setup. Again, realized by EasyTech, that has about a square meter of reactor of flow surface area with all the balance of plant around them. So the actual core of this setup is the electrochemical cell. Again, now we have not a single cell, but we can build a stack of up to 10 cell pairs. Total surface area again like 1 square meter, and we have quite a lot of volume available in as electrolyte and anolyte, and a very nice power supply to carry out these reactions at this scale. So far, we actually focused again more on the furfural oxidation. We've done experiments at with 4 cells pair, and we are reaching yields of about 50% when we consider 5HFO and maleic acid combined. Yeah, so then a bit of as I said, like once you have your chemicals in solution, then you also need to care about how to get them out and how to purify. And within the Perform project, we also looked at all the downstream processes to go from the actual electrolyte to the pure compounds. This is a bit of the process scheme that we developed. So from the maleic acid side, the first step would be an electrodialysis. Then would be an nanofiltration and a crystallization, and then we already have the sort of pure maleic acid. On the valeric acid side, we have a liquid extraction because valeric acid is now a liquid, it's not a solid, and then we have a distillation step. When we look at the first step, electrodialysis, so we need electrodialysis because we need to remove sulfur, or in general, sulfuric acid from the electrolyte. Here we have, again, with EasyTech, we built a setup, a pilot setup with a 25 cell stack, where we can actually carry out the electrodialysis and remove most of the sulfuric acid from the electrolyte. So in a way, we are concentrating our maleic acid a bit more. After that initial electrodialysis, the
That's oh, I can. Now you can try.
Sharing, right? This one. Are we back?
Yes.
yeah.
Okay.
All right.
Yeah. Use the mouse, you don't have the clicky thing.
I think it's yeah, so we, as I said, after the concentration step, we have a crystallization step to get already maleic acid crystals. We develop this entire setup to carry out this crystallization, and we even did like a test run. Well, and here are the pictures of the maleic acid that we get out. One, let's say, drawback about this setup is that the actual volume that we can use is a bit limited, and we also have a bit of material incompatibilities in the setup. So this is why we actually went for a different solution very recently. We have this new filter reactor where we can carry out different, let's say, procedures within the same setup. In general, after the pre-concentration with the nanofiltration, then we can just, you know, put this concentrated solution in here, and in here we have the freedom, for example, to, let's say, increase the temperature and apply vacuum to remove even a bit more water, so concentrate a bit more, or we can, let's say, lower the temperature with a jacketed vessel. We can lower the temperature so that we can cause precipitation of maleic acid. And because this is a filter, then we can also, let's say, wash the crystals, the maleic acid crystals, all in one setup. This is a really versatile and nice apparatus, and well, we will test it very soon. if we look at the valeric acid side, now valeric acid is a liquid, so we need different, all different separation techniques. What we came up with is this liquid-liquid extraction. So we have valeric acid is in solution, water solution, and we mix this water solution with a solvent, typically an organic solvent. This will make two different phases. And the valeric acid is more affine to the organic solvent, and it will go into the organic phase. But then you need to separate the organic phase that is rich in valeric acid from the water phase that is now, let's say, richer in well, levulinic acid, for example, that is your unreacted material. With this, we did some preliminary test with a mock solution using about half a molar valeric acid, which is more or less the solubility limit of valeric acid. And with this type of solution, we were able to recover about 85% of valeric acid that was in the mixture, using a mixture of water to organic solvent of 1.5 to 1. So this is quite nice results, and then you end up with let's say valeric acid in the order of 8% in your organic solvent. After that, you still need to, let's say, separate the organic solvent that you added from the valeric acid, and this can be done by distillation. We have a 20-liter distillation unit in-house where we can actually do this separation. And here you also have a picture of the unit, and we did again test with synthetic mixtures of valeric acid. And again, we can recover very pure samples of valeric acid. And with this, I would like to conclude about line one of Perform. And I hope I was able to show you that electrochemistry is a very versatile tool for electrification of the chemical industry. Most often you see hydrogen as a product, but in general we can carry out a lot of different reactions, including like the organic electrochemistry, which is not really very well developed so far. Even more, we actually show that we go from a few centimeters squared electric surface area to the design and construction of the full power platform with a surface area of 1 meter squared, which is kind of a unique setup well, available for industry to develop further reactions. We also have designed all the downstream processes that are needed to go from, let's say, the crude electrolyte mixture to pure compounds. And right now we're actually busy with the optimization of the 1 meter squared reactor and doing paired electrolysis to show that we can reach the productivity targets that we set for the project. And of course, together with that, we will follow with downstream campaigns to get products out that can be submitted to partners for test applications. And then we can demonstrate also the reusability of the electrolyte. And with this, I would like to thank you for your attention.
Thank you, Riccardo.
Thank you.
The membranes you're using for downstream, can you reuse them?
That's the idea. We don't have a lot of insights so far, but looking at how the system behaves on the upstream, it's likely. Because on the upstream, we don't generate a lot of, let's say, particles or humins or stuff in suspension that would actually cause the membranes to foul quickly. So I'm hoping that we can reuse them.
Can be beneficial.
Yeah, for sure.
Still have a couple of minutes for a discussion or question rounds, if there's any, on the presentations of today.
Any questions online?
And of course, all the members of the consortium are available for questions, and you know where to reach them. And you can also reach me. I think everything will be saved on the YouTube channel of Perform.
Yes.
So you can also look it back later on. And we're open to further collaborations, all of us in the consortium, also for the people online. If there's no further questions, then we move on with lunch and into the lab to show the whole pilot equipment with their own eyes. And that also includes concludes then the online session. So thank you everyone for joining us online, and hope to see you in person.